Okay, so the next step in our regression is the regression analysis, the actual, getting the regression model or equation. Once you have that, you can interpret the slope and also find out if the intercept is meaningful or not. So these three sort of go hand in hand. Okay, in addition to the correlation coefficient that we just saw, R, we can also numerically summarize by fitting a regression line to the paired data. So basically for a population, I have something like this. Y is the dependent variable. It's dependent on something in that equation. It's a function of what's in the equation. Y equals the intercept, that's the symbol for the population, intercept, plus the slope times a value of x. So x being the independent variable. And then some error associated with it because, it's the population, and if you're getting a sample, you'll have some error with it. But the way we write this equation for the sample is like this. The predicted y, that's what that hat means on top of the y, predicted y is going to be, so for the age salary example, predicted salary is going to be an intercept plus the slope times some value for x, which in this case is age. Age predicting salary. Okay, so the predicted y is the dependent variable equals the intercept plus the slope times the independent variable. So the slope is always the one leaning next to the x, sloping against the x, and that one that stands alone is always the intercept. Okay, this follows, if you recall, y equals mx plus b type equation for a line. Okay, and we saw the scatter plot for the age salary data. We actually got the regression equation there. So basically it gave us y equals the slope, 1.447, times age, plus the intercept will give us a predicted y. So if I just plug in a value of x, I'm going to get a predicted y. Okay, so that was the output for the age salary data. I can either put the variables in there or just use y and x. Age predicting salary. Okay, some other examples. Number of people dining at a restaurant times the slope plus $15.22 is going to give you the predicted cost with that many people. Amount spent on advertising times this amount plus this amount will give you what the predicted sales would be based on that advertising. The amount of square feet in a house times 150 plus 125,000 gives you a predicted home price. So regression is really powerful. It allows you to do a lot of predictions. You end up with this regression model or equation where you can just plug in a value for x and get a predicted y. Okay, and recall the insignificant relationship we had with brain size and IQ. I saw with the scatter plot and the R that there wasn't a significant relationship, so it really didn't make sense to move forward through the regression, but we can see the regression equation that we got when we did the scatter plot. It actually had a zero slope, so you'd multiply x by basically zero to get the predicted y, which kind of shows you there's no relationship there. Okay, so finally we're going to run the regression. If you recall in Megastat, that's the third step. Once you click on correlation/regression, we did the scatter plot, we did the correlation matrix, and now we're doing the actual regression analysis. Okay, so once you click on the regression analysis, it's looking for the independent variable and dependent variable. So it's kind of nice it spells it out there instead of just saying horizontal axis and vertical axis. I'm just going to leave the default at 95% confidence. That's pretty typical. Don't worry about the other options there or the residuals. We're not going to do that for this course. Residuals would help you figure out outliers, but we don't need that at this point. Make sure you select the right data. So basically, I'm going to do age as my independent variable. That's the one doing the predicting. That should come first, basically. That's the horizontal axis. The x-axis will predict the y, the dependent variable salary, salary being dependent on age. You can think of it that way. Okay, so the rest I can just leave as the default. And here's my regression output. You'll see basically there's the correlation that we've talked about before. So correlation of 0.81. Okay, the coefficients are going to be where my intercept and slope are. So you recall the equation was y equals intercept plus slope times x. So you can see that here. That's the equation, same equation that we saw before on the scatter plot. Another thing we can tell by this output is the significance of the model. So basically, remember in chapters 9 and 10 we had a p-value, and if the p-value was less than alpha, then we can reject the null and support the claim. Well, in this case, it's pretty much the same thing, where the null hypothesis is nothing's going on, and the claim is that something's going on. You're always going to be trying to prove that it's a good model, that the independent variable is a good predictor of the dependent variable. So we're looking for a really small p-value in order to accept the model, to say that the model is significant. So since this is negative exponent 6, p-value is pretty close to 0. That's going to be less than alpha, and my model is significant. Age is a good predictor of salary. And also, if this was a multiple regression problem, then all my independent variables would be listed there. And basically, I could see which independent variables are better at predicting salary. But in this case, with just one independent variable, simple regression, the p-value is going to be the same here as it is here, because the only thing in the model as an independent variable is age. Okay, so now that we have the model or equation, we can figure out how to interpret the slope and find out whether the intercept is meaningful or not. Okay, once you have the regression model from your output, you can interpret the slope and determine if the intercept is meaningful. In terms of interpreting the slope, let's look at one of the examples we've already seen. The cost of the entire dinner at a restaurant is $15.22, the intercept, plus the slope, $19.96, times however many diners you have. How many people do you have at the table? Okay, so y equals 1522 plus 19.96x. Each additional person, so as I add 1 to x, so basically if people is 1, then I'm just going to have $19.96 plus 15. If I add an additional person where x is 2, then I'm basically just adding $19.96 to the final cost. Okay, so that's how you interpret the slope. For each additional unit of x, y will increase by 1996. If the slope was negative, you would basically say for each additional increase in x, y goes down by a certain amount. Let's look at another example of interpreting the slope. For the sales example, advertising dollars times a certain amount plus the intercept is going to be my predicted sales. So basically, for each additional unit of advertising, so in this case it's in millions of dollars, for each extra $1 million of advertising, sales will go up by 7.37 million. Okay, so that's how you interpret that slope. Okay, and we can also determine whether the intercept is meaningful or not, basically by just plugging in a 0 for x and seeing if it makes sense. So in this case, the intercept is not meaningful because if I plug in 0 people, it doesn't make sense that the cost of the bill is still going to be $15.22. You know, if you plug in 0 for x, you're going to end up with $15.22. That's not observable. It doesn't make sense to have 0 people dining at the table and have the bill come up to be $15. But let's look at the advertising example. If I plug in 0 advertising dollars, I'm going to get sales of 268 million. Does that make sense? Well, yeah, if I'm not spending anything on advertising, you know, I would still expect there to be some amount of sales, and that would be lower than if I had some advertising. So in that case, the intercept is meaningful. Okay, so just to figure out if the intercept is meaningful, just go ahead and plug in 0 for x and see if it makes sense. Okay, the most powerful thing about regression is actually using it for prediction, like I had mentioned before. So I found that my regression model for salary and age was y, basically predicted salary, equals the slope 1.447 times x, or age, plus the intercept. So what's my predicted salary for a 25-year-old? All I have to do is plug in 25 for X and see what my predicted salary would be. So in this case, 25 times 1.447 plus 8.191, and those are in thousands. So $44,366 is the predicted salary with this regression equation. How about the home price example? If this is the regression model, home price, or Y, equals intercept of 125,000 plus 150 times the square feet, which is X, what is the predicted home price if the square footage is 2,000? All we have to do is plug in that value for X, 2,000, into the square feet, times 150 plus 125,000 gives us a predicted home price of 425,000. Here are some other examples for the intercept and slope. So we had the sales and advertising one. Here's another one. Drug cost equals 410 plus 550 times dependence. So basically each extra dependent raises the mean annual prescription drug cost by $550. That's interpreting the slope. In terms of whether the intercept is meaningful, an employee with 0 dependents averages $410 in prescription drugs. That makes sense. So there is a meaningful intercept. For rent in square feet, each extra square foot adds $1.05 to monthly apartment rent. The intercept is not meaningful because no apartment can have 0 square feet. Miles per gallon and horsepower, each unit increase in engine horsepower decreases the fuel efficiency by 0.079 miles per gallon. Okay, so there's an example of where you'd have a negative. So negative slope means the predicted Y is going to go down by that amount. And the intercept is not meaningful because a 0 horsepower engine does not exist. Doesn't make sense. Okay, some other examples of making predictions. We saw the sales and advertising example, but let's say drug cost and dependence. If an employee has 4 dependents, the predicted annual drug cost would be $2,610. Basically just filling in 4 for the number of dependents, filling in 4 for X. Predicted rent on an 800 square foot apartment, we just fill in 800 for X, use the equation to get the predicted rent of $990. And if an engine has 200 horsepower, the predicted fuel efficiency is 33.42. Just filling in the 200 for X. So really powerful regression for making predictions. Okay, now another thing that helps us kind of make an end result or conclusion about X predicting Y, or the independent variable predicting the dependent variable, is R squared. R squared is basically what percent of variation in Y is explained by X. So the higher the R squared, the more is being explained, the better X is at predicting. Okay? It's called the coefficient of determination, but research articles typically just report R squared instead of saying coefficient of determination. It tells the proportion of variation in Y, so let's say salary, explained by X, age, for example. Okay, so it's a value between 0 and 1. Oftentimes it's turned into a percentage, so it can make a little more sense to the reader. So basically, if my R squared is 0.76, 76% of the variation in Y is explained by X. Or another way to say it, X explains 76% of the variation in Y. Okay, so let's look at some examples. We saw in the output for the age and salary data that the R squared was 0.663. That's important to report. It means 66.3% of the variation in salary is explained by age. So basically, that's pretty high considering the fact that there's so many other independent variables that could go into predicting salary. Things like experience, education level. Okay, so yeah, fairly high considering all the other variables that may predict salary. And it might lend the question, what might go into the remaining 33.7%? If I have 66.3%, yes, that's high, but I'm not quite at 100% explanation. So what about the 33.7%? So you'll often see in research articles where they talk about the R squared, they might say, avenues for future research is to consider what might go into the rest, the remaining? What other independent variables could be possible? Here's an example I saw in Psychology Today. It was an article about genius, genes, and gusto, how passions find you. And if you look deeper into the article, you see this person from UC Davis estimates that between 22% and 36% of the differences in creative achievement in the arts and sciences may be explained by natural endowment. Now notice the wording. That's an R squared. Without getting the eyes glossed over of the people reading it by saying R squared or coefficient of determination, they're just explaining it, spelling it out. R squared is between 22 and 36%. Natural endowment explains 22 to 36% of the variation in creative achievement in the arts and sciences. So that's how they've kind of translated R squared into a journal that people can read. Here's another example that I saw in Self magazine. You have it in you. Your DNA determines a lot more than your eye color. Researchers have pinned down nearly 40 gene patterns that help predict your workout mojo. In fact, one study found that genetics accounted for 62% of the differences in exercise behavior. Notice that wording. In fact, one study found that genetics accounted for 62% of the differences in exercise behavior. That's how you would report an R squared. 62%, and then they're going into examining the other 38% down here. So 62% factors ruled by genes, other factors, personal motivation and goals, living in a pretty location, listening to music, having active friends, living in a place with sidewalks and public transportation. So that's an example of reporting the R squared. Okay, so I know we've already talked about the p-value representing whether the model is significant or not, but I like to end with that because it's kind of a good way to kind of segue into a summary of findings, the overall model. So here's a summary of our findings for the age salary data. We've already talked about the p-value showing that it's significant. Age is a good predictor of salary. We saw the strong positive correlation when looking at the scatter plot, but we didn't have a number associated with it though. So we ran the correlation analysis, and that was a 0.8, and it was highlighted, so we know it's a significant correlation. It's also pretty close to 1, so we would have an indication that that is significant, even if it wasn't highlighted. After running the regression analysis, we saw that the amount of variation in salary that is explained by age is 66%. That's the R squared. We also know the model is significant because the p-value is below the level of significance. So typically the null hypothesis is that nothing's going on. We have to prove that something's working here for the model. So the claim or alternate hypothesis is that there is a good model, that age is a good predictor of salary. So if we have a really low p-value, we can reject the null and support the fact that we have a good model. Because the slope was 1.447, we can say that for every year increase in age, salary will go up by approximately $1,447. Okay, so that's interpreting the slope. Is the intercept meaningful? The intercept is not meaningful because it doesn't make sense to plug in 0 for X, for age, and still have someone making $8,000. Okay, so overall, age is a good predictor of salary, but it would be interesting to see what other independent variables might predict salary, such as years of experience or education. And that's where you might have a multiple regression, where you have more independent variables predicting salary, such as amount of experience, education level, as well as age.